Hello, everyone. So I'm a Marie Curie Fellow, and like pretty much everyone else in this room, we are all related to the Marie Curie actions. But what if I told you now that we're going to see Marie Curie in a whole different way? So let's try to do something very different. Let's make this screen full screen now. Maybe? Can we make this full screen? Oh, there we go. So let's do something different. We're going to look at the center of this circle, and I need you to do that for 30 seconds. I know that it's dizzy and it's not pleasant to look at, but it's going to be worth it, so just bear with me. It's another 5 seconds. Keep your eyes in the center. The less you move your eyes, the better this is going to work. So keep looking at the center, keep looking, and now here is Marie Curie again. So what's going on? Well, this is precisely the question my research tries to answer. I'm a neuroscientist, and I study the part of the brain that deals with vision. I try to understand how do we see. Well, that's easy. We open our eyes and we just see. Well, if we think about it, it's not such a simple process. If I was like a robot or an artificial intelligence device that I was trying to analyze this image, I would start in the first pixel and start analyzing it pixel by pixel. By the time that I arrive to the third row here, my 5 minutes will be over and I will be kicked out of the stage without even starting to give my talk. So this is not a good approach for the visual system. We cannot try to analyze all the information that's out there. So the brain does something very different, which is to construct our perception of the world. It takes very minimal information as fast as possible, and it uses its past experience to interpret the image, to make a very educated guess of what's out there. And most of the time it works great, and we just see. And in some instances where stimuli are particularly strange, which in this case where I made you look at something not natural for a long time, then the system got messed up, and it made the wrong assumption that Marie Curie was in expansion. So this is the type of, in fact, so we're studying the brain, and for us neuroscientists, visual illusions are indeed a very useful tool, because by studying where the system fails, we learn a lot about how it works. And this is the type, they are also very useful as educators, because as you saw, they are interesting and fun and intriguing. So they are a very good starter to go to high schools and start talking to students about research. And I've been doing this now as a part of a new program by the Marie Curie Actions Office called REACT, Researchers at School and University. And what this is trying to do is to bring Marie Curie Fellows to schools to talk about their research project. So the goal of this program, which is now in a pilot phase, is to promote research careers among youngsters by explaining why research is important for society and why the European Union invests in it, and also dispel stereotypes about researchers and research. We are normal people. We wear funny t-shirts. So it also brings Marie Curie to schools and closer to society, which is another important point. To become a good scientist, you really need to be in touch with the society that you are trying to address the problems. So the pilot has been running since May, and it has been highly successful. It has already reached over 850 students in high school and middle schools, and over 400 students at universities. And something important about this, when we go there, is not only that we tell them about our research, and we try to do some presentation that can be understood, but you can see now that we are pretty good at doing that, and explaining things in lay terms, but we also talk about our career paths, about how do you become a scientist. And to me, that was fairly interesting and very personal, because I don't know about you, but when I was at high school, I really didn't know what I want to do next. A few of the students in the class knew they want to be doctors or lawyers or engineers, but many of us knew, oh, I really like maths and physics, I find philosophy very interesting, biology is something that really attracts my attention, but is that what I want to do forever? Is this the career I want to do? So by talking about our career paths, for example, in my case, I studied physics and then I switched to neuroscience, and how fields are actually quite interdisciplinary, because in research it's very important to integrate different points of view. So to understand the brain is not only about medical doctors and biologists, but we really need the inputs from physicists, engineers, computer science, who know a lot of information and communication of information. That's exactly what the brain is doing. So we need the perspective of all these people to try to understand something as complicated as the brain. And bringing all this to the class, I think, really helps them to understand what are the possibilities, and also how their first choice they're going to make now is not as dramatic as they may think, because life goes on, and there are many times to flip paths and finish up in a very different place. As the previous speaker said, she started with architecture and is now in cultural heritage and many other cross paths. So another feature of this is that it has reached students from all around Belgium, and that's important. They didn't just focus on the students in Brussels or next to the high schools next to the big universities. Those schools usually have interactions with the universities, but it's important that the program reaches out everywhere. So to take the time, even if it's a bit more time and cost effective, to bring researchers to high schools in more rural areas that don't usually have this type of access. Also, we have gone to schools in not so favored neighborhoods like Molenbeek or Scherberg in Brussels. So we are also trying to, before we were talking about the divide and the dissemination of knowledge and spreading science around. So that's also important in the socioeconomic divide. So that's how, by bringing this to all types of schools, we'll make science more accessible to all types of people. So I just want to finish by thanking my PhD advisor, Susana Martinez-Conde, a Kirsty Grant, one of my mentors at the CNRS, for teaching me that doing outreach and science communications is not something you do on the side, away from the bench, but it's really an integral part of your job as a researcher. And also thank the Marie Curie program for reinforcing this idea and allowing me time, forcing time of my fellowship to do this type of research. And not only did I learn that's very important and an integral part, but it's also a very rewarding one. Here is an example of a thank you note that I got from students in a very special high school we went to that was inside of a hospital where they have the interns that had mental disorders related to anorexia and other eating disorders. And I got this thank you letter from one of the students that really made my day and showed how all this was completely worth it. So by seeing this type of thing, I hope that when REACT finishes its pilot stage in Brussels and goes out to the whole Europe, all fellows will be willing to participate and go out to high schools. Thank you.
Thank you very much, Xoana. Do we have any questions from the audience? Either about her research in particular or about her work with the REACT program or the REACT program in general? Okay, I have a question. You mentioned that you started off in physics and then moved to neuroscience. Did you find that a difficult transition to make?
So, no. If we think about it, the brain has over a billion neurons. That's more neurons than people on Earth. That make over 1 trillion connections. That's more connections than stars in the Milky Way. So this is a really complex net of information that's being transmitted through electrical impulses. So all this really speaks to physicists. They are actually the specialists in circuits. So in that sense, it's not a hard connection to make. However, socially, it may look a bit weird, especially if you come from a country like me, like Spain, where these transdisciplinary things are not so established as in other places, and the flexibility in career paths are not so common. So at that point, where I started saying that I was going to do a PhD in neuroscience, people I typically work with or my colleagues were really like, wow, are you going to do that? You're always going to be behind the biologist in over the theory. But as soon as I entered neuroscience, I started finding that in all labs, you have a very big mix of biologists, physicists, engineers, computer scientists, and it's not an issue at all.
Great. Any other questions from the audience? So I have another one for you then, about the REACT program. In terms of communicating your science to school students and to university students, what's the biggest thing that you've learned about communicating science, and do you think that it'll be a useful skill for you to have as you move throughout your career?
Well, the most useful skill is definitely adapting your discourse to the person you are talking to or the group you are talking to. And that's definitely a very important skill, not only to go to the high school class, but to go to speak to this Brussels audience or to a very specialized audience about my research or to a future employer. So that's definitely a very versatile skill that's very useful to have. And really when going and talking to the students, even the different students in different places are different. So another thing I really like when I do this is that these are not linear presentations where I just go there and do whatever I have prepared. You have to be very open to listen and to look how they are reacting to your slides, and you immediately adapt to try to get their attention and talk about what they are interested in.
Okay, thank you.